Right. We are back live. So I was working on problem 8 when my computer crashed of Avnica 2025. Um, I'm not completely sure. My computer's not crapping out. Okay, we seem good. We are good for now. Okay, when he finished, I was just realizing that I have a misunderstanding in the problem. So what I was trying to do is make the first 1,000 connections, but I wouldn't make a connection if two pieces were already in the same component, right? If they were already connected, I was not going to make that connection. But um, that's not the problem here. So we can actually make cycles. Uh, oh, I don't know about cycles. Maybe we don't make cycles, but the point is we can connect to the 10 shortest connections. Um, yeah, the 10 shortest connections. So that's not what I was doing. I was doing the 1,000 shortest connections. Connect together the 100 pairs of, wait. Am I just supposed to connect 10? Your list contains connect together the 1,000 pairs of junction boxes. No, we're supposed to connect the 1,000 closest. So what I was doing was I was connecting the 1,000 closest, like the nearest first, but I was skipping over connections if they were already part of the same unit, right? So like, I don't know. To illustrate, let's say we have a graph, and this is already, let's say the next shortest connection is going to be here, right? Um, well, that's not a good example. Let's say the next shortest connection is going to be here, right? I would skip over this connection because I'd be like, well, we're already in the same circuit. We're already in the same circuit, so I'm not going to do that. Um, and then I would keep adding connections, right? But you can't add 1,000 connections. 1,000th connection is always going to be, like by 999, the circuit is fully connected if you're connecting it in that manner. How's my stream quality, by the way? My bitrate good? Am I live for real this time? Okay, it's working all right now. Great. So we are supposed to make, yeah, we just connect together the 1,000 pairs. So here's the code where I'm connecting those in our states. We connect. This is how we choose an edge to connect. We can choose this in a different way. We just pop off the next edge. So basically, this is about edge onto remaining is just equal to candidates. We just take the next candidate. And from that point on, everything should work. Now, I know this much of the code runs in just a few seconds. As long as there's not an error. That's not an error. That's just a warning. 39300. That's not the right answer. That answer is too low. So 39300. Let me check that this also works for the example. Like the reason I thought I was fine earlier was that it was working on the example, but I think it's a coincidence that none of them were connected. We've got a weird bug here where I can't get to the first line of code. It does look like my PC is stalling a bit though, right? Let me know as soon as my stream is stalling out. Let me try and Okay. Did I figure it out? Am I live? Okay, my CPU is no longer throttling. I think I figured out what it is. So when my power supply, okay, close WSL window. Try that again. And we'll load up VS Code. I'm glad we at least have a culprit. So I do run this from a laptop. It is a workstation class laptop. So it is pretty beefy. But it does still have laptop behaviors like that when you unplug the power supply. I think I just need to restart WSL altogether. Sorry for the technical difficulties. Now when we were coding this up, I did remove that constraint that they are not already in the same circuit, right? Wait, the next two junction boxes are these two. Yeah, see, this is how I read this. When I read this line, I said because they were already in the same circuit, we're not supposed to connect them. That's how I read that. But the truth is that just nothing happens, which, all right. There's now a single circuit with 3 junction boxes and an additional 17, which contain only 1 junction box each. Oh, hold on. Maybe nothing is supposed to happen. Okay, wait. Hear me out here. I think I have another interpretation of this problem. So we're supposed to look at the 1,000 shortest connections. We skip it if it's already a circuit. Um, and then at that point, we get all those connected components. Or I don't know, like go ahead and make the connection. I guess it shouldn't matter. You'd still get the same components. Although I'm not sure my connected component method deals well with cycles. It should. It has a set of visited, so it should deal all right with cycles. Okay, opening up the admin code repo. Here we go. So my updated code, I'm just gonna give it a shot on the example. Make sure I'm understanding the problem. Um, all right, we gotta change this to. You do hear me? Okay, you hear me? You see me? Or are you saying you understand me? You understand why I made that misunderstanding? The video is stuttering. Okay. Well, as long as the audio is good, the video can stutter a little bit. Let's run this. In fact, this is the worksheet are still spinning up. So what we're going to do is just run the day8.scout file. Yeah, I'm on Windows and WSL. So I run all my code on the Linux side, and I connect into it with VS Code. So to make the appropriate change here, we have edges remaining 20 components. So there are 400 possible, roughly 400 possible connections to make. If you make 20 while skipping things that are already in the same circuit, then that would connect the whole thing. Okay, I think my worksheet is about to be up and running. I'm going to continue working on the actual code. Yeah. Yeah, that should add up to 11. I've done that here before, right? So like my tests here have that. There are 11 circuits, and this adds up to 11. Yeah, that's the thing with the example. I did check the size of the components, of each of the components. I also checked the sum of all of the edges. So if you add up the sum of all of these, the sum of the sizes of all the components, then it should be, well, all 20 of those, because you have a component, you know, all of the nodes are split between those components, right? So that adds up to 20. Components.size is 11, and we've seen that. Boxes.size is 20. So we've seen and verified all of this. Right. Now this is a change. So since we changed the code here, that's changed from 12 to 11, which is interesting. Let's change it back. So, okay, my previous implementation gives the right answer. The fix is not working, so I think I'm misunderstanding the fix then. 20, 11, 40, those are numbers we want to see. And the component sizes, yeah, so the component sizes changed too. So that's not good. I guess we are supposed to skip those. Here, I can show you my sizes on the example, and it is indeed 5, 4. There's two twos in there. We could sort them. That's sorted dot reverse for each print line. And we should see 5, 4, 2, 2, and a bunch of ones after it reloads. Okay, so we could refuse to make the connection if it's already connected. And just take 1000. So these are our candidates. They're already sorted by distance. We're connecting at most 1000 edges, so let's read the problem very carefully. It says, your list contains many junction boxes. Connect together the 1000 pairs of junction boxes which are closest together. What do you get if you multiply together the sizes of three largest circuits? Okay, so we're just going to take the 1,000 pairs. So these are the edges. We're going to take 1,000. So these are the 1,000 pairs that are closest together. Um, and we'll only connect edge if it's not already connected. So instead of next edge, what we'll do here is val AB. This is what we're connecting. And then we have the remaining edges to connect. In fact, at this point, this becomes a fold left. I'm not gonna modify this code. I'm just gonna write a new bit. So we'll leave that as is, but comment it out. So we'll make a new definition of states, and we can just do this with a fold left. So we'll do edges dot take 1,000 dot fold left, and we still start with that same default adjacency graph. And now our case is going to be just the adjacency graph. So here's edge. I'll put up here. Oh, no. Adjacency, and then there's a new connection. And there's a new edge, A and B. All right. And we're going to connect that edge, but conditionally. Let's just not bother connecting it if it's already connected. So if connected, A and B are connected in the adjacency graph, then we just return the same adjacency graph. Yep. Otherwise, we do connect. We connect that edge in the adjacency graph. Okay, so there's our new states code. Let's give that a shot with the example. Edges. There we go. This is no longer an iterator, so the end state, oh, this is just the end state. End state. And we'll leave this content.code up here above in case we want to revisit that. Okay, let us compile. Oh, wait, this would be take 10. We're taking just the 10 closest edges. All right, 20, 11, 40. Good, that works. So let's try that on the actual code. So we're taking 1,000 edges. And give it a second to run. Take a look at our I want to see my metals window. Here we go. Okay, we're evaluating the worksheet. Great. 39,400. Oh, I was off by a little bit. 39,400 is still too low. And 400 low. Okay, well, we still have that many boxes. We have 1,000 different components. That's sketchy. We should still have 1,000 components after making a bunch of connections. So let's take a look at our end state. Um, so that's the adjacency graph. And then we create various components. There are 159 components. Well, no, that actually does make sense. This sum should be up to 1,000. That's good. Um, Interesting. So we have taken 1,000 edges. This worked on the example. And we only made, well, depending, we didn't make 1,000 connections, right? Because some of those were already connected. But we looked at 1,000 edges. Let's look at our connections again. So these are all the edges, right? So these are all possible combinations of A and B, and we're sorting them by distance, right? So the shortest ones appear first. There are that many edges. We're not going to use all those edges. We're just going to use 1,000 edges. We're filtering out the things that are already connected. If they're already part of the same connected components, we're filtering them out. I may could print a graph of this. Let's make a list of our components by size. So 788, 10, 5, 4, 4. Okay, there's one huge component that's 788. 788 by 10 by 5. Um, and that's 39,400. Put this into here. Yeah. And we tried 39,400. That's wrong. So I'm still misunderstanding the problem, aren't I? Right? Do you get what I'm thinking here? Because apparently what I'm thinking is wrong. I'm solving a different problem. But coincidentally, the problem I'm solving is the example problem, yeah? How do you calculate the number of shortest connections in your biggest component? The number of shortest, what do you mean? I think you're trying to hit me, but I don't understand your question. So your biggest component has, well, your biggest component is going to have at most, well, it's going to have, so my if my biggest component here, in this case, is 5, it's gonna have at least 4 connections, right? If we're just connecting everything and not filtering it out, then that's a little bit different. Right, if we skip this line here and just always connected the edges, that would change our answer a little bit. Um, it does continue to work for the example. Oh, it's the same answer. There are just more edges connected in the adjacency graph, but it shouldn't make a difference, right? So if I run that for the puzzle input, see if I get the same answer. Oh wait, 10. We need to be taking 1000. Yeah, we're still. So we make all those 1000 connections, and we still end up with 159 components, the 3 largest sizes of which connect or multiply to 394. Um, so maybe there is a bug in my component building code. Is it? I mean, this is pretty simple, right? We take we take a box that isn't assigned to any component yet, right? Then we do a flood fill search to gather its component, and then we diff out that component, all the elements in that component from our list of unsorted, and then we continue down that list of unsorted, gathering a piece. Um, so this is pretty straightforward, and I do like the way I've written it. I think it's clean. Um, so I'm not going to spend too much time trying to debug that. This is a singular component. Maybe the singular component we're getting is too large. What's our code for making connections? You know, I think I can just delete this. We're not going to come back to that. We make a connection by updating the adjacency graph symmetrically. So we update A to include B, and we update the adjacents of B to include A. That seems pretty reasonable. This next edge we're not using anymore. I will just comment that out for now. Because we were filtering out things that are already connected. Connected should, I'm going to distinguish connected from adjacent. So connected just means it's in the same circuit. In fact, I'm going to rename it. This is now same circuit. Same circuit. Okay, that just tells us if two are in the same circuit. All right, I think I'm understanding the problem correctly. Overflowing, for fuck's sake. You got it. You got it. I think you got it. Thank you very much. That did seem like a small number. Okay. We're taking the product of a big list of ints. Wait. No, that's probably not it, because if you look at this, 788 by 10 by 5, that's not going to overflow. Right? We're just multiplying 3 numbers, all of which are going to be less than 1000. because no component is going to be larger than 1000. That's the largest possible component. So it isn't an overflow. Distance. Oh, I guess some of these could be pretty large. Right. Okay, well, let's do it this way. I'm just gonna make those all dot too long. Dot too long. Oh boy. Good catch. If that's it. Yes, your distance calculation. Hey, look at that. Look at that. it was integer overflow. Thank you. That's true. You don't need the square root, right? You can just normalize it with that. Yeah, we'll just make that quick change. All right. Good catch. Square root's going to be inefficient. As long as we have a metric, right? Okay. Let's look. No, that wasn't the issue. The first issue was that I was not connecting things if they were already in the same network, right? And I was still trying to make 1000 connections. It was this line. If we're already in the same circuit, nothing happens. I was like, oh, so you're not supposed to make any connection. But you still make 1000 connections. It's just that you don't skip any connections. Ah, I want to blame Eric for that one. I just misunderstood that completely. So part two, let's check our delta. The L's were right. They definitely don't have enough extension cables. You'll need to keep connecting junction boxes together until they're all in one large circuit. Yeah, we just do 999. We already did that. Continuing the above example, the first connection, which causes all the junction boxes to form a single circuit, is between those two junction boxes. Okay. They also need to know how far those junction boxes are from the wall so they can pick the right extension cable. Multiplying the x coordinates of those two junction boxes produces. Okay, so what is the final edge is what it's asking. Keep connecting until they are all connected. Okay. Well, now at each step, we have to compute the components. And then we have to update the components. I'm wondering if I'll have to like refactor this to make it more efficient. But we can do the easy thing, which is just to continue connecting edges. So we could take all states by taking a scan left. And then end state would be 1000. Well, end state equals all states 1000. We just want to make sure ends one still works. 1 second, my monitor disconnected. It'll be right back up. Well, I can't see my monitor. My computer can. Okay, we're back. Cool. It is a day of tech issues. Um, so about all states. So we're just gonna take edges dot scan left, um, and we just connect these edges. And we could name this. We can do some cleanup later, actually. So we should still get ands one there. Um, this will need to turn into a def. Def find all components. Or we'll just def components. For that, what do we need? This uses end state. We need an adjacency graph. Map point to set point. That should just be a type alias at this point. And we're going to use that adjacency graph here. Okay. So now the components of end state, that should stay the same. Now for ans2, we want edges.scan left. We can take index where. So we could take all states. Well, we want that in a separate step. So all states.index where that state, the components, components, dot size is equal to 1. So we'll just call it index. And then final edge would be the edge at that index. So edges at that index. And we multiply their x coordinates. So ans2 got val a, b is going to be the final edge. And then a dot x times b dot x. Okay, I'll let that run. Now, I do worry that finding all the components at each step is going to be needlessly expensive. And what we might have to do instead is at each step, we grow the components instead. So we merge two elements of that set. Okay, timeout reached. We could let that, do I dare let that yellow in the background? We might dare. We might dare. The issue was the power cable, right? We don't need to print all of those. Are there any other print lines you don't need? Okay. Boylan, hey, how are you? How'd your night go? Oh, I totally remember you, of course. Oh no, is that a raid? Thank you for the raid, Boylan. Okay. Um, what do we do? We're just gonna let that run in the background, right? Famous last words. I'm less worried this time. So SPT, we're gonna run main 2025.day8 because it might not be that much longer. And let that run while we refactor this search. Um, so we'll still have a state of the adjacency graph. I like having that around. It's very handy. But we'll also have a state. Let's give this a name because we're going to reuse this multiple times. So this is going to be empty edge graph. Now empty edge equals that. And honestly, this bit here, Roland, thank you for follow. We can just, yeah, we'll leave that code as is. If we change the order of those, we could just use underscores. Um, and we don't want this code here. We want a new search. And that new search will be, I suppose, an unfold. So our state is an empty edge. And then a list of components. And we just start growing all of those components. Is that more efficient than computing components every time, really? Because we are going to be like removing things from that list when we merge components, right? I suppose we could just have a check. Instead of making all the components and checking that size is 1, we could say, you know, is an adjacency graph fully connected? And we could short circuit that search. So def fully connected. We have an adjacency graph, which is a map from point to set a point. And I guess we just take any element and we count. So we could just take edge dot, well, no. We do still have to do a, you have to get a component. So edge dot head dot, we'll get a key. And we'll get the component of that key. So component of a in edge dot size is equal to boxes dot size. Okay. So now this code. Oh wait, we found an answer. You found an answer. It took 2 minutes, but there's an answer. Uh, too high. Um, that's a little bit concerning. So those last two edges were wrong. Maybe it's off by one, and I'm just off on the edges by one. Um, we should try it in the example. But we can still do this. So components.size is equal to 1. We say fully connected. Yeah, the index were fully connected. And let's try that on the example. Part 1 can be 10. No such element exception. Oh, we don't have anything that's fully connected. Well, what is all states? Well, we take all the possible edges and we just connect them, right? So we shouldn't get to the end of that. All right, I'll be right back. I need to go to the bathroom. Okay, so what happens? What happens here? We definitely don't need this function anymore. We're still getting the correct answer for ends 1. So we know that index is working properly. And what is our final edge? Oh, right. We don't get there because we have next on an empty iterator. All states edges is a list. Where exactly is the iterator? I suppose we're doing fully connected. Component, right? We call component to build a component. There's no iterator here. I'll follow the stack trace. Iterator.next in fully connected. So when we check if something is fully connected, oh, we get head. We get head of an empty set. of an empty adjacency graph. Okay, right. The very first one's going to be empty. Dot drop one. Okay, so our final edge is what, 2 points? So 117, 168, 530, 216, 146, 977. Okay, so we're not getting the wrong index. Let's switch back to this then. And we can change this back to part 2 as well. What is our final edge? Maybe we did have an overflow. I don't think so. Well, hold on. Maybe we did have an overflow because we have like 5-digit numbers or something. 10-digit numbers in the billions. Okay, yeah. A dot x dot too long. Dot too long. Um, it's not running as fast as I would like, so I'm going to do that in the unlimited source file. ABRV8D. Thank you for the raid. Were you doing admin of code? Right, let's let that run again. It has been a year. I spawned in just in time to be ever present for AOC. You've been working on it the last 2 days. Well, good to see you again. Oh, we have a lot of print lining going on. We didn't want that. This is going to continue to keep trying to run. I need to halt that because apparently it takes about 2 minutes. 2 minutes to run. We'll stop the print line. No, that's not the worksheet. Okay, this is too many things to print. And we run that again. And with Scala as usual. So are you using different languages again this year? I like that about your stream. So for day after connecting the boxes, there'll be no box left alone? Yes, for part 2. Hey, and we have an answer. That looks different than the answer we got last time. That doesn't look that much larger. It looks smaller, in fact. We can plug it in, but I'm skeptical. Oh, that is it. Cool. We didn't proceed further. Okay, well, we got it. We got it. How long did that take to run? Is it still like running in the background or something? Okay, we finally got there. Yeah, we had a huge misunderstanding of the problem for part one. Ugh, I don't dare to look at the leaderboards. We'll have a peek. We'll have a peek. Um, so before tonight, oh, it hasn't updated yet. I was neck and neck with Rascal 2 and who else? Temporalis. I probably dropped quite a bit today. Um, yeah, well, I no longer top the Scala leaderboard. And has this updated yet? They are slow to update this year. Let's find someone to raid then. I'll have to make it up next 3 nights. Um, and I don't know. You should add something to my Am I Being Stupid list. I don't know what to add based on that. Um, there's a data structure that's really helpful for this problem. For which part? Part one or part two? Um, it might be something that I'm supposed to know already. Okay, well, is it a structure that helps you keep track of the components? 1 second. I'm getting a call, and then we'll find someone to raid. Okay, let's find someone to raid. Um, so in part one, we only make a specific number of connections. Yeah, you only make a specific number of connections. Well, you don't. Well, yeah, you make 1,000 connections. Even if they're already in the same circuit, you make that connection. Man, that was a line, confusing line. Union find. Okay, yeah, union find. I'm familiar. I don't have an implementation of union find. Kruskal's algorithm. Hmm. Yeah. How many people got caught up by that line in particular? I can't be the only one who this one here, nothing happens. I can't be the only one who read that as don't make a connection. Ah, yeah, so you shouldn't waste an extension cable. That line too. Waste an um yeah. Yeah, it was confusing for sure. I totally read it as don't make a connection too. Oh well. I mean maybe it is don't make a connection, but then you're not making 1,000 connections, right? If you don't make a connection, but you still have to make 1,000 connections, then you're gonna end up with the whole thing connected. Okay, we find someone else to raid. Yeah, it doesn't count as one connection or something. Eric, Advent, Twitch. Who's still alive? Um, is Bad Cop still working on it? We can also we rated Alka yesterday. Yeah, let's raid Bad Cop. Let's see this done in Bash. I wouldn't know. I wouldn't know how to do any of these in Bash, to be honest.
Matt dot albedo color equals.
I do have to run. So let's
How do we blend
I have a Discord if you want to chat more about the problem, or we
color
can chat about it
dot
tomorrow.
oh,
So see you around.
row mix two colors GD
Raid
script.
Bad Cop. And thanks for sticking it out with
Color?
me through the technical issues tonight.
Is that
Oh
real?
man, what a pain.
I think you can just do it like this.
All right.
Yeah.
Have a good one.